All right, so this video is going to be on implicit differentiation. And basically what implicit differentiation is that we are going to be differentiating an equation such that y is not isolated or on its own side. So if you look at the examples up here, on the left side, we always have either it's the output y or the output such that it's g of x or h of x, so on and so forth. But what can happen is that these equations can be written in a way where y or the output is not isolated by itself or written as an explicit function or in explicit form. So what we're going to look at in this lesson is how do we differentiate those types of equations, and they are called implicit differentiation. So implicit, it can also mean intertwined, which means that you'll see x's and y's or t's and v's and different types of variables. They're going to be mixed in with one another, but you still have a method to differentiate these types of equations. Now, when we use implicit differentiation, it's basically an extension of the chain rule, and you have to recognize that as we go through these steps, okay? So just a quick review. Which of the following functions would the chain rule have to be applied in finding the derivative of y? So recognizing when to use the chain rule, you basically have to recognize composite functions, okay? So if we take a look at this, if we were to rewrite y, this is y is equal to f of x to the power of 1/2. So the outer function would be the square root. The inner function would be f of x. So if we were to differentiate y with respect to x, then we bring the 1/2 to the front. That means f of x is now to the power of negative 1/2. And then we take the derivative of the inside, which is f of x. So that would be f prime of x. Therefore, we would use the chain rule for a. B is not a composite function. The derivative would just be dy dx. It'd be a one-step. dy dx is equal to f prime of x, which means we would not use the chain rule for this. This one, you can see it's another composite function. So if we were to differentiate y with respect to x, the 1/5 would come to the front, and then we would leave the f of x the same. 1/5 minus 4/5 will be negative 4/5. And then we'll multiply with the derivative of the inner function, which is f of x becomes f prime of x. So we would use the chain rule for this one. And then lastly, we have y is equal to f times f of x. If we differentiate with respect to x, we just end up with 5 times f prime of x. So this would not require the chain rule. Now, what we are seeing here is a form of the product rule. However, when you multiply with a constant, that one of the terms becomes 0, so we just keep the coefficient there and then multiply with the derivative of the function. All right, so this one should have been A and C. Now going a step further, number 2 says differentiate the explicit form of the equation y equals 1 over x, and then also differentiate the implicit form xy equals 1. So basically, why we're doing this is still preparing us for related rates using implicit differentiation, because we will be using algebraic manipulation to change equations and whatnot so that we can solve for basically what is in dy dx. Now, differentiate the explicit form, we've been doing that. We just don't say it because it's implied because y is already isolated. But at the top, all these examples, they are explicit. Okay, so let's go ahead and do what we've been doing. So we have y is equal to 1 over x. And to differentiate this easily, we can rewrite it using an exponent. So the derivative of y with respect to x, that's going to be, we'll bring down the coefficient, so it's negative 1. And then negative 1 minus 1 is going to be negative 2. So the derivative is going to be negative 1 over x squared. All right, and then the second part says differentiate the implicit form xy equals 1. Okay, so we have x times y is equal to 1. Now this one is implicit because y is not isolated. Okay, we have x times y. However, you could write it in a way where y is isolated. You could divide both sides by x, but not every single implicit form will be that easy to manipulate to where you can isolate y. There will be times that you simply can't isolate y. So understanding how to implicitly differentiate is going to be important. Now, if we look at this, we do have x times y, so we can use the product here. So I'm gonna have the same function, but I'm gonna do a rewrite, okay? We're gonna have x times y of x equals 1. And that's because y is in terms of x. It is y of x, so x is the input, and we are differentiating with respect to x. So if we look at this as far as the product rule, we'll call xf, and then we're going to call y of x g. So just recall, for the product rule, we have f prime times g plus f times g prime. Now, whenever you see differentiate, I guess we should have explicitly said solve for dy dx, because that means you'll have to isolate dy dx, which is what you're going to have to do with related rates. So it's going to be good practice. But if we don't say it in the directions, solve for dy dx or solve for dy dt, then usually you won't have to do it. But in this case, we will, so we can practice it. All right, so f prime is going to be the derivative of x. The derivative of x is 1. And then we have times g, which is just y. And then plus, we have f, which is x, times g prime. So g prime is going to be the derivative of y with respect to x, okay? And this first part here, we took the derivative of x with respect to x, which is equal to 1, okay? The variable that we are differentiating with respect to makes a huge, it changes what it's going to look like for each variable. So if you're differentiating a variable with respect to that same variable, you will just directly differentiate. However, because we are differentiating y with respect to x, g prime is just going to be dy dx. So we have x times dy dx. And then we're using implicit differentiation. So we're going to differentiate 1 as well. The derivative of any constant will be 0. All right, so from here, if we try to isolate dy dx, I'm going to end up with x times dy dx is equal to negative y, and then dy dx is equal to negative y over x. Now, solving for dy dx, you'll want it to be in terms of x, right? So we need to substitute something in for y such that it's written in terms of x. If we go back to the original equation, if we isolate y, we have y is equal to 1 over x. So I can use that and substitute it into y, okay? So that means we have 1 over x divided by x, and all of this is negative. All right, we can multiply with the reciprocal of the denominator. So we have negative 1 over x times 1 over x, which gives us negative 1 over x squared, which is the same answer we got when we were differentiating the explicit form. Okay, so this is how implicit differentiation works, right? So let's take a look at a couple more examples. Number 3 says find g prime of x for each function. Okay, so this is just another chain rule exercise. So g prime of x, we're going to bring down the 3, the power, and then we have f of x, and then we go down a degree to 2. All right, so the inner function is f of x, so we're going to multiply with the derivative of that, which is f prime of x. All right, part B says g of x is equal to y cubed. Okay, so with these, when it says g prime of x, that means we are finding the derivative of g with respect to x, okay? So with this example, we could just do the chain rule straight up, okay? Because f is in terms of x, we were able to just differentiate that function, okay? Now, if I were to rewrite this using Leibniz notation, it would be dg dx is equal to 3. That would be f of x, and then times the derivative of f with respect to x. Okay. Now with this one, we're going to just go ahead and use Leibniz notation again. Y is a function of x. Okay. So y is a function of x. So we are going to be differentiating with respect to x. So I'm taking the derivative of g with respect to x. We will use the power rule first. So we have 3y squared. Okay, so now this is where the chain rule comes in again, just like part A. All right, so we are taking the derivative of y, which is the inner function, with respect to x. And this is going to be g prime of x. Okay, another way to write this is just g prime of x is equal to 3y squared times y prime. Okay, but Leibniz notation really helps to see how the variables are working within these implicit forms. Number 4, find dy dx in terms of x and y for each equation. So when it says find dy dx, that means you have to isolate dy dx, okay? So let's go ahead and implicitly differentiate this. It's implicit because we do not have y isolated. And this is one where you would have some trouble trying to manipulate it by isolating y because you have a y and a y squared. So let's go ahead and differentiate. So just keep in mind that variable y, we are differentiating with respect to x, but these variable y's, they are in terms of x. Okay, they are functions of x. All right, so we're going to go ahead and differentiate with respect to x. So 5y, this is going to be 5 times, and we are differentiating y with respect to x. So that is just dy dx. There's no chain rule like we did in part B up above, so we just straight up differentiate y with respect to x. Now this next part, we will have the chain rule, okay, because we have a composite function. We have the square and the y, okay? So we'll use the power rule first. So I have my coefficient. Bring down the power rule. I have 2 times y, and that's to the power of 1, okay? Now I'm going to take the derivative of the inner function, which is y, and we are differentiating y with respect to x. And then we have the plus. Now, since this variable is in terms of x, we are differentiating x with respect to x, we will just do 4x cubed. So it's not chain rule, it's not a composite function, it's just x, all right? This was composite because it's a function of x, y in terms of x. This is just x, okay? Now, if we were differentiating with respect to y, then the roles would switch. We would not see dy dx here. Instead, we would see dx dy over here. Okay, so it depends on what variable you are differentiating with respect to, but I know it's x because of the instructions, okay? All right, so now that we have differentiated, we now need to clean it up and we have to find a way to isolate dy dx. So we have 5 dy dx is equal to, we have 6y dy dx plus 4x cubed. All right, so let's get the dy dx on one side. So I have 5 dy dx minus 6y dy dx is equal to 4x cubed. From here I can factor out the dy dx because I need to isolate it. So we have 5 minus 6y is equal to 4x cubed. And the last step to isolate dy dx is to divide both sides by 5 minus 6y. And we found dy dx. All right, part B, a little more complex, but you'll follow the same procedures. Now we have 3xy minus 1 is equal to x minus sine y. Okay. The biggest obstacle we will have in this is the 3 times xy. That's going to be your product rule. So there's a couple ways that you could combine these. You can move, well, the easiest way would just be keep the 3 with the x, but you could also put it with the y. So I'm going to say that 3x is f, and then y will be our g. And if you recall, product rule is f prime of g plus f g prime. Okay, so f prime, f is 3, therefore f prime will be 3. And then g is just y. And then plus f is going to be 3x. And then g prime, we are differentiating with respect to x, okay? So when I took the derivative of 3x, it was already with respect to the same variable, so I can just go ahead and use the power rule there. However, for y, we are not differentiating with respect to the same variable. Therefore, if I want to differentiate y, it'll have to be with respect to x. So if it's a degree 1 y, there's no chain rule, okay? The y just becomes dy dx. Now over here, whenever your y is to a degree or to a power that's greater than 1, you will have to use the chain rule because it's a composition function, okay? All right, and then the minus 1, that will be minus 0. All right, when we differentiate x with respect to x, that'll just become 1. And then the sine y, this is going to be chain rule again, all right? Because our input is not x, it is y, which is a function of x, we will be using the chain rule, okay? So the derivative of sine, that is going to be cosine. And since we differentiated the trig, the inner function will remain the same. Now we're going to multiply with the derivative of the inner function. The inner function is y, okay? And we are going to differentiate y with respect to x. So if you look at that sine is the outer function, while y is the inner function. So we have to use the chain rule there. Okay, since we're solving for dy dx, we have to get dy dx, or all the terms with dy dx on the same side. So we'll have 3x dy dx, and then we will add the cosine y dy dx. And just to make it clear, that dy dx is not inside of the argument for the trig expression. Okay, so I have my 1, and then I subtracted the 3y from both sides. From here, we can factor out dy dx. So we're left with 3x plus cosine y is equal to 1 minus 3y. And the last step is to divide by 3x plus cosine y. So dy dx is equal to 1 minus 3y divided by 3x plus cosine y. All right, so number 5 says find the equations of lines tangent and also normal to the circle at the given point. Okay, so you guys had a question like this before, and I was shocked when I didn't see any pictures. A picture can help a lot. All right, so we have x squared plus y squared is equal to 169, and we are going to use the point at 512. So we have a circle with a radius of 13. Okay, and the point 512 is going to be in the first quadrant, so somewhere over here. All right, and we want to find the equations of the line tangent and also normal. So let's focus on the tangent. The tangent line is going to be the blue line, okay? And we talk about this all the time. What 3 items do you need for the equation for a tangent line? You need your slope, you need your x-coordinate, and you need your y-coordinate. We already have the x-coordinate and the y-coordinate. Those are provided. But now we need our slope, all right? And our slope is going to be dy dx, okay? The derivative of y with respect to x. So to get that, we're going to have to differentiate this equation. Okay, now we are differentiating x squared with respect to x, which means this is not chain rule. This is just going to be power rule. Okay, so we will have 2x. Next, we're going to differentiate y with respect to x. Now, because we are not differentiating with respect to the variable in this term, you will be using the chain rule for this, okay? So we will have 2y, y being the inner function. Now we will differentiate that inner function with respect to x. So we'll have dy dx. And then the derivative of 169 is going to be 0. So to get the slope for this tangent line equation, we need to isolate dy dx. Okay? So we'll have 2y times dy dx is equal to negative 2x. And it makes sense to see that negative because the blue line it clearly is going down, so it has a negative slope, so that's good to see. Next, we'll divide by 2y. When we divide by 2y, we just end up with negative x over y. So that is our equation for the derivative of y with respect to x. So how do we find out what the slope is at this point? Well, you have to evaluate dy dx at that point. So this isn't complete here. Actually, let me rewrite these because they're a little slanted. So my slope is going to be dy dx. We said our x sub 1 was 5, y sub 2 was 12. So this is not complete. If I want the slope at 512, I have to evaluate the first derivative at that point. So Leibniz notation, again, you also saw this before. This means we are evaluating the first derivative at 512. Okay, it's similar to evaluating f prime of we'll say 5, but we can't use this for implicit differentiation because you require both x and y. So this notation doesn't help. Okay. This is why understanding Leibniz notation is important because it helps a lot with implicit differentiation. So when we evaluate the first derivative at 512, we'll go ahead and plug it in. So the x-coordinate is 5, and then the y-coordinate is 12. So that's the slope at 512. So the tangent line, you don't always have to include that subtangent. It just helps because we have to find another tangent line equation. So the slope is negative 5 over 12. The x-coordinate is 5. And then the y-coordinate is 12. So now the question also states also normal to this circle at the given point. So normal means perpendicular, all right? Or another word is orthogonal, right? We played around with that word very rarely in pre-calculus, but orthogonal, normal, perpendicular, they all mean the same thing. Now, there is not much work you have to do for this. However, before we go into that, what we're looking for now is this. We are finding the line normal at this point, okay? Or to the circle at that given point. So it's creating that 90-degree angle there. So now we're going to find the red line. So this is the blue line. And now we're going to find the red line. Now, to find the red line, to get the line normal to the circle at that point, you just have to use the opposite reciprocal of the current slope, okay? So normal means you use the opposite reciprocal. I would remember this. Opposite reciprocal. So let's do it. So we have y, I'll say norm for normal. That's the red line in the graph, is equal to, opposite means we'll make it positive, reciprocal means we'll flip the denominator and the numerator, 12 over 5, x minus 5 plus 12. All right, number 6, differentiate with respect to t. Treat x and y as functions of t. So what that means is we have x is actually x of t, and then y is actually y of t. So that means when we differentiate, you're going to be using the chain rule for every single variable because they are technically composite functions. I don't see any t's, so we're not just going to use the power rule. They will all be chain rule, okay? So if I wanted to look at this, you don't need to write it like this every time, but this is technically x of t, that is going to be cubed, minus x of t, minus we have y of t cubed. Whoops, there's another parentheses, equals 12. And we are going to differentiate all of this with respect to t, okay? So if we differentiate x of t cubed with respect to t, we do have chain rule, so I'm going to use the power rule first. So I'll have 3x squared, okay? And I'm getting rid of the t's now, okay? 3x squared, so x of t is the inner function, so now we will multiply with the derivative of that function with respect to t. So we're going to multiply with the derivative of x with respect to t. Now over here, we are just taking the derivative of x with respect to t. And the last one, it's going to be the same as the first term. So we will use the power rule first. So we will have 3y squared times the derivative of y with respect to t. The derivative of 12 is 0. And the problem doesn't ask us to find dx dt or dy dt, so we can just leave it. All right, last problem. So same thing, but now as I analyze this, we have a product rule. Whoops, we have a product rule. So we'll say that 2x, that will be f, and then y cubed is going to be g. And just recall we have f prime g plus fg prime for our product rule. All right, so starting with the first one, again, we are differentiating with respect to t. So for x's, we should see dx dt. For y's, we should see dy dt's. So we have our coefficient. We bring down the power 3, and we have x squared. Now we are going to differentiate x with respect to t. Minus, now we have our product rule. All right, so f is 2x. All right, so when I differentiate 2x with respect to t, remember the coefficient doesn't do anything. It's just there, okay? So I have my 2. So essentially what I'm doing is I'm differentiating x with respect to t. Because if you think about it, if you have 2x and you're differentiating this with respect to x, what are you left with? Just 2, okay? That's because you have 2 times dx over dx, which is just 2, okay? Now with this one, we're differentiating with respect to t. It's the same exact thing, okay? So when you differentiate this, you have 2 times dx dt, okay? So it's the same process. Okay, so now that's the first part of the product rule, so that's f prime. And then we have g, which is going to be y cubed. So this is f prime, and then this is g here. And then we have, actually, I need to put a parentheses here because we have a plus, because we're subtracting this entire product rule. The next part is going to be f, which is 2x. And then we are differentiating y with respect to t. Okay, so we'll do the power rule first. So we have 3y squared. And now we will differentiate the inner function, which is y, with respect to t. Then we'll close the parentheses. And then minus, we'll do the same thing we just did for y. We have 6y to the 5th times dy dx. And this will all be equal to 0. Just to clean it up a little bit, we have 15x squared dx dt minus 2 actually, let's put the dx dt last. So minus 2y cubed dx dt plus 2x 3y squared. Well, if I'm distributing that negative, it should be a minus, right? Minus 2x 3y squared dy dx. Oh my gosh, that should be a t. We're differentiating with respect to t, not x. Sorry about that. dy dt, and I did the same thing over here as well. So this is why it's good to always go back through your work just to make sure you don't make those same mistakes. 2x 3y squared dy dt minus 6y to the 5th dy dt is equal to 0. All right, that's implicit differentiation. The next video will be related rates, which are the application problems. I hope this was helpful.